good insights to inviting me here approximately 1 year ago, anticipating that there might be a Nobel Prize for LIGO. What he did not anticipate is that we would detect a binary neutron star merger, which was an equally important event, I would say. So what I hope to do in this lecture is to give you a general sense of what gravitational waves are, why they are important to detect, how we detect them using these really sensitive instruments called interferometers, and what we've seen so far, and why it really is the nueva ventana, the window on the universe. All right. As Doug hinted in his talk, at least what I could understand of his presentation, we look at the universe through different types of instrumentation. Here in Chile, there's a rich tradition of astronomy, observational astronomy, optical astronomy. But we also use things like particle accelerators. So the picture in the upper right is the Large Hadron Collider. Smash subatomic particles together at very, very high speeds, approaching the speed of light. We look at the mess that's made, the particles that come off, and that tells us something about the fundamental forces of the universe. There are also two other modalities, one which Doug mentioned called neutrinos, which carry information. They're very hard to detect, but they tell us a lot, for example, about supernovas, about nuclear processes. And then there are also cosmic rays, which are very high energy protons, are basically particles that produce showers that can be detected. And so these instruments over the past hundreds of years, starting with astronomy, have told us how the universe works. They have been the key to understanding how the universe works. However, the universe has a dark side to it. All right? We now know, for example, that most of the universe is made up of something called dark matter, and even more of it is made up of dark energy. All right? So how do we study those kinds of things? All right? I'm going to tell you about a new window on the universe that may not reveal dark matter or dark energy, but it could tell us things, for example, about the birth of the universe, the Big Bang. And these are the gravitational waves. So let me start by showing you what kind of telescope LIGO is. This is a picture of the Ligo Hanford Observatory. This is in the United States, all right? And it looks nothing like the telescopes that you've seen before. So you should think of this as a completely new kind of telescope. And it's a telescope, to use an analogy, that doesn't see, it doesn't detect light. It's a telescope that hears. It actually hears the sounds of colliding black holes. And I will literally prove that to you later on. All right, I'm going to start with my favorite scientist, Albert Einstein. Albert Einstein has made huge contributions to physics. All right, one of his most famous contributions is special relativity. All right, I suspect you're all familiar with this famous equation, E equals mc squared. What does that mean? It means that energy and mass are equivalent. And the equivalence is this constant c. This is the speed of light. And light travels very fast. All right, so this equation takes matter and energy and says they're all one thing. You're probably not familiar with this equation. You don't have to understand it, but what it basically says is that space and time are also mixed. If I'm moving at a constant velocity relative to somebody else at rest, all right, the way I measure distance and the way I measure time are different. My time is not your time if I'm moving at a different speed. So this was a revolutionary theory. And I think Einstein knew that. This is a great picture of Einstein, right? He's sort of saying, I told you so. All right. Now, you probably have never seen this equation before. All right. This is an equation that is much deeper than the equations that I showed you before. This is general relativity. So in special relativity, Einstein takes mass and energy, puts them together in a theory. Takes space and time, puts them together in a theory. General relativity takes mass and energy, space and time, and puts them all together in the same theory. This is a very complicated mathematical equation. I'm not going to spend any time going through it, but I'm going to tell you what this equation means. It basically says that space and time is equal to matter and energy. But there's a constant, all right? Physicists love constant. I'm a physicist. So Einstein's theory of general relativity says that space and time and matter and energy interact. And it does so through a very interesting process called geometry. All right? We all learned about geometry. So let me show you a picture here. And I'm going to try and explain general relativity to you in one slide. All right? Look at this green for a second. Now I want you to forget about the green and just look at the sun and the earth. All right. You've all heard of Isaac Newton. Isaac Newton postulated a theory of gravity over 400 years ago. That theory of gravity, very powerful theory. It explains why planets orbit around stars. It explains why stars are in galaxies. It tells us how to launch rockets and put up satellites. It's a very predictive theory. And basically what that theory says is that I have a big mass over here, and I have a small mass over here. This is the sun, this is the earth. And the reason the earth is orbiting around the sun is because there's this force called gravity that basically is proportional to this mass times this mass, and decreases as you separate the two masses by the square of that distance. So the further away the sun is from the earth, the less the pull of gravity is the square of that distance. Right? That works really well. What it doesn't tell you, and this is where Einstein comes in, and even Sir Isaac Newton knew this, how does the sun know that the earth is there? How does the earth know that the sun is there? Einstein told us that nothing travels faster than the speed of light. So how does this guy know that this guy is there? If I have two objects that are half the universe apart from one another, all right, they know they're there, but it takes time for the information to communicate. And that's where Einstein came in. So Einstein introduces this concept of geometry through that equation. So now look at the green graph, and you'll see the little squares. You probably all remember coordinate systems when you were taking algebra and geometry. And when you're far away from masses, the geometry is flat. It's what we're used to. We would call it Euclidean geometry. But when you put a massive object, in space, it changes the geometry. It warps space-time. Placing matter in geometry changes the local geometry. And you can see that here, that the space is bent. Now I'm showing this in 2 dimensions because it's hard to show in 3 dimensions. And you can see there's a little dimple here where the Earth is. The reason the Earth is orbiting around the sun is not because there's a magical force called gravity. It's because the sun has changed the geometry such that the Earth, when it wants to move, it thinks a straight line is actually orbiting around here. So if I were to put a little, marble around here, the marble would go in that direction. More importantly, if the sun were to magically disappear somehow, all right, basically the space would recover to flat, and it would take 8 minutes, which is the light travel time of the sun to get to the Earth, and then the Earth would fly off. So this theory was revolutionary, but it explained all the anomalies that you couldn't explain with Newton's theory. For example, bending light around stars and things like that. All right. I can summarize it very, very simply. This is what general relativity says. It says that space tells matter how to move, and matter tells space how to curve. Right? That's it. So you now all completely understand general relativity, right? Right. But there's another aspect of this theory that's fascinating, and it's why I'm talking to you today. Objects that move, all right, and objects that accelerate produce ripples in space-time. Because space is no longer static, it can curve. If I put objects in space, in this case these are 2 big black holes, and they're orbiting around one another, what will happen is they will generate ripples in space-time. This is an artist's concept. I'll be more specific in a moment. But what's happening is, as they're accelerating, they're losing energy because they're stretching and stretching space. And because they're stretching and stretching space, they're radiating, their orbit collapses, it decays, and eventually these two objects will collide together. So that's what we're trying to see here. All right. Okay, so now, how do you measure them, and why are they so hard to measure? What really is a gravitational wave? A gravitational wave is a strain. It's a change in length per unit length. Now, this is a concept, if you took physics in high school, maybe in college, you might remember this. If I take a bar and I push on the bar, all right, the bar is compliant and it will actually deform a little bit and get a little bit shorter. And the distance that it shortens depends on how long the bar is. So that's what we're after here. Suppose I were to generate a gravitational wave behind the board, and I were to send that gravitational wave right towards you. What would you see? Well, you'd see this, all right? Look at this one, don't worry about this one for now. At the gravitational wave stretching this way, on one part of the gravitational wave you would get a little thinner and a little taller. On the other part of the gravitational wave you'd get a little shorter and a little heavier, all right? And this would continue. All right. Now, this equation is the key. Understanding that equation is the key to understanding how you detect gravitational waves. So if I look right here, where I've sort of arbitrarily put a crossing point, what happens if I look there? Well, if I look there, you see that the strain, the change in length, is quite small. But if I look out here, it's much bigger. That's because I'm much further away. So the idea here is that you want to have large separated distances to measure these strains. Right? That sounds easy, but it's not. All right. And Einstein knew it wasn't. This is a copy of his paper where he predicts gravitational waves. All right. I promised you no more equations. I'll just say this thing here called A is what I just called delta L over L. All right, and if you translate the last sentence here, what Einstein said in this paper where he predicted this phenomena is he said, then A, that's the delta L, that's the gravitational wave amplitude, must have a virtually vanishing value in all imaginable cases. When Einstein tells you you shouldn't look for these things, he's probably right. All right, so this was predicted in 1916. Right? So for almost 100 years, it was impossible to detect gravitational waves. And the reason was that we didn't have the technology. We didn't have the capability of making measurements with the precision that we needed. So let's try and make a gravitational wave in our laboratory. This is a mad scientist. He's truly crazy because he's going to take two 1,000 kilogram objects, separate them by about 1 meter, and he's going to spin them around 1,000 times a second. All right, now, I wouldn't want to be in this laboratory because these things would fly apart and kill people, but okay. How big a gravitational wave did he make? All right, this big. All right, this is an awfully small number. All right, to put it in perspective, all right, if I were to go to the edge of the universe, all right, this is much, much smaller than a centimeter and even than a millimeter. Right? So it's a very, very tiny number. All right, so you might say Einstein was right. We should just not worry about this. We should go off and do something else. All right. Well, it turns out that nature produces objects that naturally generate gravitational waves that are maybe a little bit bigger. All right, so here's the delta L for these two objects. These are two neutron stars. I'm going to say more about them later in the talk. But basically, they're very compact objects. They're about 25 kilometers in diameter. They have a huge amount of material in them. They're 1.4 times the mass of the sun. If I were to take a teaspoon of a neutron star They're basically giant atomic nuclei. 1 teaspoon would weigh 1 billion tons. All right, so these are ultra, ultra dense objects. All right, they produce a strain like this. And so you might say, you know, that's still pretty small, it's still pretty hopeless, maybe I should go off and do some other kind of science. It turns out that with lasers and with the right technology, we can actually detect this kind of event. All right, so how do we detect it? All right, so I told you to have a challenge. And by the way, let me go back to that. Making a measurement of that precision would be the same thing as measuring the distance from our sun to the nearest star, Proxima Centauri, which is about, I think, 3.5 light years away, roughly 3.2 light years away, to the thickness of a human hair. So the precision which I have to measure to be able to see this kind of effect is basically equivalent to measuring the distance between our sun and Alpha Centauri to the thickness of a human hair. All right, so that gives you the level of precision that you need here. So how do we do it? Well, we build these things called interferometers. I'm going to spend a little bit of time telling you about what the interferometers are. First, let me introduce the Ligo detectors to you. There are 2 interferometers. This one is in Hanford. This is the one you saw earlier. This one is in Louisiana. They're separated by about 3,000 kilometers. They are very large installations. There are about 190 people that I work with at Caltech and MIT, and there are about 1,200 scientists all over the world from almost 100 institutions that basically make it all work and make it come together. Here's the picture in Livingston, and now I want you again to remember the delta L over L. You might ask, so this is where most of that action happens, but there are things happening up here. This is 4 kilometers long, and this is 4 kilometers long. So that's the L, all right, in our measurement. So you can then go back and say, well, I know that delta L over L has to be 10 to the minus 21, 0.0000 20 times and then 1. How big do I have to make a measurement of delta L? And the answer is about 10 to the minus 18 meters. All right. Now let me just give you a perspective there. That's about the thousandths of the width of a nucleus of an atom. All right, so we're trying to measure that kind of precision. Here, this one you've seen before. This is the Ligo Hanford Observatory. It's in a completely different part of the world, but these instruments are absolutely identical. All right. Now I'm going to tell you how we do this experiment. How do we detect gravitational waves? We start with a laser. I'm going to show you a movie. We start with a laser. The laser is going to produce light. All right. The light is going to get split into 2 equal components. So half the light will go in this direction. You can think of this as a mirror, but an imperfect mirror, where half the light goes in one direction, half the light goes in the other direction. All right. The light comes back. When it recombines, the light will come back towards the interferometer unless a gravitational wave is present. So let me run the movie here. So we start with the laser beam. So the wavelengths are color-coded, and this is why this experiment works, because we have very, very precise wavelengths. The light comes back, and when there's no gravitational wave present, right, the light goes back towards the interferometer, and there's destructive interference here. So the light interferes in a bad way. But when a gravitational wave passes, basically one arm stretches, the other arm compresses, and the light constructively interferes. So at this point, you're basically taking that stretching and compressing of space and turning it into light, which then goes on to a screen, or in this case, a photodiode. So what the interferometer does is it basically records the signal of a passing gravitational wave. Again, that analogy with sound, as you'll see in a moment. This is what it really looks like. This is, let me go back here. What I'm showing you is what's in this building right here. All right. Everything, all these things are big vacuum systems, so there's a huge amount of technology that I'm not going to go into, and engineering. Actually, the reason LIGO works so well is because we have wonderful engineers. who are very good at telling physicists and astronomers, you can't do that, you have to do it this way. And that happens a lot, and that's why it works. So the laser itself is actually over here. So that picture I showed you, or that simulation I showed you before, the beam splitter is right here, I think. No, it's right here. The beam splitter is right here. This is one arm of the interferometer, and this is the other arm of the interferometer here. And just because my background is in lasers, I'll show you the laser. Doesn't really look like much, except for that you can't really see the people working because the laser is very sensitive to contamination. So this is a very, very clean environment. You have to dress up completely in white too. So it's hard to know who you're working with sometimes when you're doing this. Okay. All right. So that was sort of a very basic introduction into interferometry and how we actually try and measure these things. We basically use the fact that light is a very precise ruler, right? And that we use the interference of light to detect the gravitational waves. So now let me tell you what we detected. So the first gravitational wave event was recorded on September 14th, 2015. Remarkably, it happened right about the time that we started operating. We spent a lot of time building detectors and making them work. And when we flipped the switch and said, okay, we're going to start looking for them, all right, it just so happened that at the right time, about 1.3 billion years ago, all right, these two black holes were doing their ballet of death. And I'm actually going to show you a movie of this here. So what we detected came from this source. So let's start with this person, this guy, this black hole. 36 times more massive than the sun, 210 kilometers in diameter. What is a black hole? The name says it all. It is basically a region of space that it has been so compactified that no light, if you get beyond this black area called an event horizon, no light gets out. Right? And what happens is it usually comes about from, say, the collision of the explosion of a big star, a nova, a supernova. And if the supernova is big enough and it leaves enough mass, nothing can overcome the force of gravity, and all the mass just collapses behind that curtain called the event horizon, and it actually turns into pure space-time. So all the identity, you don't want to fall into a black hole because you lose your identity. You're no longer who you are, you're no longer protons or neutrons, you become pure space-time. All right, I don't recommend it. Okay, so, and they're compact. They're even more dense, if you will, than neutron stars. All right, so this one is 210 kilometers in diameter. So, just to put this in perspective, this is basically you could fit one of these in maybe not length in Chile, you can fit a lot of them in Chile lengthwise. This is the second black hole, not quite as big, not quite as massive. And what I'm going to do is I'm going to show you, that equation that I showed you at the beginning, that complicated equation, you can solve those equations. And we have colleagues at Caltech and Cornell who solve those equations and visually produce this rendering by solving those equations. And all the stars that you see behind are just there for reference. All right? And the reason that the stars look distorted is because the gravitational potential here, the curving of space, as you've seen, is so big, so large that the light's getting bent. All right, so let's play the movie. This is slowed down 100 times. So here we go. So the stars are orbiting around another. The reason they're orbiting is they were bound together, but they're losing energy because they're radiating gravitational waves. You can see the star fields are changing because the gravity is changing and the bending of light is changing. They're getting closer together. They're speeding up. They're getting closer together, and eventually their event horizons will merge. They'll touch. And you see that big burst, that big vibration. That was the last burst of gravitational waves, all right, coming out. And what's left behind is a really, really big black hole. So this black hole happens to be 62 solar masses. Now, if you remember, I told you, I'm going to make you do some mathematics in this. You're going to have to think. Right? We started with something that was 36 solar masses. We added to it something that was 29 solar masses. That's 65 solar masses. What's left behind is only 62 solar masses. What happened to the other 3 solar masses? They were turned into gravitational waves. So at the moment of collision, the equivalent of 3 times the mass of the sun was converted into energy. Right? And that process, pure energy, that process took less than a second, about 2/10 of a second. Right? This event is a very, very, very bright event. Okay. All right. When that happened, this collision was brighter than the entire universe in electromagnetic radiation, by about 20 to 30 times. So 20 to 30 times more power was radiated from this black hole collision than is radiated at any given time during over the universe. So that's a pretty amazing thing. Now I want to show you what we actually really detected. So that movies were great, but the movies came from these waves. And if you look at these waves, they look like little squiggles, but to a gravitational wave physicist, they look marvelous. Because you can actually see, as the orbit decays, that the frequencies are increasing, and then eventually the black holes merge, and what's left behind is nothing, or just a big black hole that's not doing anything. So this is exactly what you would calculate and expect for a black hole merger. And the other thing is that the 2 different detectors at Livingston basically saw the same thing. If I were to overlay these in the right way, you would see that they're identical. Right? So that's quite amazing. And as this points out here, the amount of strain that we detected was 4 times 10 to the minus 18 meters. I'm sorry, the distance was 4 times 10 to the minus 18 meters. All right, so how big is that? Well, let me show you. Well, here is the data together. All right, so you can see that the data is very consistent. When I saw this the first time, I was blown away. I've been working on this field for 20 years, and when you see something like this, it really it's life-changing. You're like, wow, this is why I've been doing this for so long. All right, now let me give you a sense of how small this signal is. So that's a hydrogen atom. So this hydrogen atom, we're going to zoom in on it. So that's the nucleus, that's a proton, that's 10 to the minus 15 meters. Now we're going to zoom in more. Right. And now, as the gravitational wave passes, proton shrinks and grows by 2 1,000ths of a proton diameter. So this is what we're measuring. Right. And it's a clear, clean signal, and that's just let's see. This was a big deal, and the Nobel Prize Committee thought so too. So they awarded Ray Weiss, Barry Barish, Kip Thorne the Nobel Prize. And it's interesting that they can divide the prize up. So they gave half the prize to Ray, and a quarter of the prize to Barry and Kip. I'm sure they don't really care. I mean, they all won the Nobel Prize. Interestingly, I listened to the announcement actually the morning after, and the Nobel Committee was actually quite, I would say, gracious in awarding the prize, because it pointed out that there were a large number of people who worked on this project, and so I think they had to give the prize to 3 people, but I think they were aware of the fact that a lot of people made major contributors. What's really interesting is that you can go on the Nobel Prize winning website and you can see the most popular physics laureates. Well, there's Albert Einstein again, he's always number 1. Right? All right. But Ray, Kip, and Barry are number 2, 4, and 6. And in between them are Niels Bohr and Marie Curie. So anyway, this was something that we were all very, very honored by and humbled by. Now, let me go back because I want to play this again. Now I want to come back to this analogy that I said that these gravitational wave detectors do not see things, they hear things. Right? I'm going to play for you the signals. Actually, the signals have been very cleaned up. Of 2 of the signals that we've seen. The one that I just showed you, the big the black holes that were colliding, and then a different event, slightly less lower mass black holes. And you'll be, well, all I'm doing is basically playing what came out of the interferometer. So here we go. Oops, it's not playing. What's going on? Oh well. All right, I can sing it for you. All right, if this had worked right, all right, what you would have heard is whoop, 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 whoop. All right, these are called chirps. right? And these chirps are actually basically an up chirp in frequency. It's too bad we couldn't hear it because it really is quite nice to hear. Maybe I'll turn. Maybe it's just the sound is off. Try it again. No. All right. Well, technology has failed us. We can detect gravitational waves. We just can't play the sounds for you. Anyway, it's quite remarkable. You can go online and you can hear this also. So, all right. Let me move on. And now let me talk about the event that just happened, and that actually Chile played a major role in this event. It's the detection of a binary neutron star. All right, when you have two neutron stars colliding, I showed you what that looked like earlier. LIGO can see those. All right. This comes back to a theme I think that Doug introduced. It's called, it works? I can try it again. All right, thank you. Let's give it a shot. There. More volume. Turn up the volume. You can kind of hear it. This will be better. There. All right, so what you heard, just barely, but you did hear it, all right, was basically the frequency changing as the objects, the black holes, get closer and closer to one another, all right? And the fact that you can hear it, all right, tells you something about the nature of these kinds of events, right? That these big, huge black holes collide and they produce sounds that go whoop. All right, that's it. That's what our detector hears. So it's quite remarkable. Okay, so coming back, this is the idea of multi-messenger astronomy, as Doug introduced. So when black holes collide, all right, all we get is a whoop, not much else, because black holes, by their nature, do not produce light. All right, when neutron stars collide, because they're matter-rich, they're made up of nuclear material, neutrons. Basically, they will collide with a bang, and they will produce an incredible burst of light. And so you can follow this dance of the neutron stars and the subsequent collision by looking in gravitational waves, but also in visible and infrared light, also with X-rays and gamma rays, and also in radio, and even perhaps in neutrinos. And giving this talk, I've given this talk a number of times over the past year. And when I used to give this talk, I used to say this was the future of gravitational wave astronomy, and it would probably be a few years before we get to this future. I was totally wrong. All right, it was actually on August 17th of this year where we saw the first binary neutron star collision. So where do neutron stars come from? Supernova produces an object that's very, very compact. That's about 25 kilometers. Again, made up of pure nuclear matter. Just for scale size, this is California. This is the San Francisco Peninsula. This is the San Francisco Bay. And this is 1.4 solar masses. So these things are, again, I want to give the impression that they're very compact. Right? And so you can imagine when two of them collide, and collide at nearly the speed of light, about a third of the speed of light, all right, the amount of energy that's released is amazingly big. And there's a lot of nuclear reactions that happen in this nucleon-rich environment. So how do we know where these things come from? All right. Well, it turns out that one interferometer is not very good at detecting the location of a gravitational wave. I sort of use the analogy that interferometers are microphones. Right? But if we have multiple interferometers, the two LIGO interferometers, and an interferometer that has just started operating in Italy, so that's over here, we can basically triangulate. So a gravitational wave source will be received at different points of time, all right, in different locations on the Earth. And that allows you, just by looking at the time difference, to localize the position of the sky. All right, that's very important. For the experts in the crowd, we don't do that localization very well, and that's something that you'll see here. This is the signal that we saw. So this just compares the waveform from the neutron star, that's this guy right here, to all of our black holes. Right? And you can see that this is a much, much longer signal. In fact, it's so long that if I kept playing it for a while, you'd all go to sleep. So I'm going to actually skip through that. All right. On August 17th, the Fermi Space Telescope detected a gamma ray burst. Right? At the same time, or nearly the same time, the LIGO and Virgo interferometers detected a signal that looked like it came from a binary neutron star. And it came from this point in the sky. And if you zoom in on that point in the sky and you say, where is the source located? All right, the SWOPE telescope, which is located not that far from here, it's Las Campanas, all right, discovered that it came from this galaxy. Right, that's NGC 4993. Right. This was a remarkable event because you knew exactly where it came from, not because of the gravitational wave detectors, but because of the optical telescopes following up that lead that we gave them. This unleashed what happens to be one of the most intense astronomical campaigns in the history of astronomy. Over a 12 or 13-day period, 70 telescopes all over the world, and including 7 space satellites, all right, looked at that galaxy to try and look at that event. And you might ask yourself, why would so many people take all their telescopes and look at that event? And the answer is because it was unique. It was the first time that we'd ever been able to see a binary neutron star collision detected by gravitational waves, but then emitting light across the electromagnetic spectrum. Right? You can see here, these are all the telescopes. In fact, Chile was probably the best place for this because the event was actually in the south. You can also see there's a little dot here. All right? That's the ice cube neutrino detector. So basically over all 7 continents, we have telescopes looking at this event. All right? All right, so this is going to be, I can't translate this for you, but you can read it yourself. But what it basically is going to tell you is that we're going to see this event over all kinds of different parts of the spectrum. All right, here is what we saw. All right, so this is the production of gravitational waves. All right, the neutron stars come together, they collide with a bang, and they produce this cloud. This is nuclear-rich material. So, and it's very energetic and it's very dense. So there are all kinds of nuclear reactions going on. All right. Now, I want to ask a question of you. Right. The question is, where do elements come from? Right. Well, hydrogen comes from the Big Bang. Helium comes from the Big Bang. Most of the air we breathe comes from supernovas. Where do heavy elements come from? And it turns out that up until now, we speculated, but we didn't know that most of the heavy elements, gold, platinum, uranium, all right, come from the collision of 2 neutron stars. All right. So in yellow here, and this data was all obtained because we were able to watch this event with all these telescopes. Everything in yellow, this is the periodic table, everything in yellow, all right, basically came from neutron stars. So most of the gold in the universe comes from the collision of neutron stars. All of the uranium in the universe, where's uranium? There it is right there, comes from neutron stars. So what you just witnessed was not the collision of 2 binary black holes. It was in fact an elemental factory that's producing new elements. All right, so all the gold that you're wearing, chances are, was produced in a binary neutron star collision billions of years ago. So this is a remarkable piece of science because we now know something about the nature of elements from gravitational waves and from observational astronomy. Right. What else can we hear? Well, I've already showed you that we can see these neutron stars and black holes colliding. We also think that we can detect supernova. All right, when a star explodes, if it's spinning around, we expect that it produces gravitational waves. That's very exciting. Very hard to model that. A spinning neutron star itself, when I showed you that image of the neutron star spinning around, we might be able to see gravitational waves from that. Perhaps the most exciting source of gravitational waves, but the one that's probably hardest to detect, is the residue of the Big Bang. So the theory of the universe that physicists and astronomers believe is caused basically inflation, where at the moment of the birth of the universe, the space-time expanded, leading to, and it's still expanding, leading to the universe that we know right now. Turns out that gravitational waves are the only way you can actually look back to the moment of the birth of the universe, and that's quite exciting. So this is something, I think, besides the black holes we've detected, besides the binary neutron stars we've detected, when we actually are able to see this kind of event, and we may not be able to see it with LIGO, there may be others that we'll see. This will be very exciting. Let me close with telling you why this really is a revolution in astronomy and why it's only the beginning of the revolution. So I've spent the better part of an hour telling you about all the interesting things that we've detected with LIGO. All right? But there are other gravitational wave satellites and detectors going up. All right? In the next decade, probably late in the next decade, maybe early in the 2030s, there are also detectors that can detect longer wavelengths. This is called LISA. This is the Laser Interferometer Space Antenna. All right? Our arms are 4 kilometers. Its arms are 2.5 million kilometers. So it can detect gravitational waves that have periods of minutes to hours, and therefore it can look for much different and heavier sources. Beyond that, radio telescopes, all right, can look for gravitational waves that have periods of years to decades. It can look for supermassive black holes colliding. Imagine galaxies colliding where the black holes, right, basically merge into an even bigger black hole. This is what the radio astronomers will be able to do using pulsar timing. And finally, this is how we're going to get at the Big Bang. All right, there are detectors that are being built in the South Pole that will detect the gravitational wave background through the way it interacts with light. So this is an exciting view of where the universe of gravitational waves is going to take us in the next 20, 30, 40 years. So it really is exciting. I'm really delighted to be here. And I'll tell you that the Nobel Prize, really all these people in this picture can rightfully say that they're proud that they were part of the team that got the Nobel Prize. I always have to point out when I give a talk that science doesn't happen because it's easy. It happens because it's hard, and it happens because it's expensive. So we get our money from the National Science Foundation, which has funded this really remarkable project over the last 40 years. So I will start there, and I will tell you that we think this revolution has begun. Thank you.
Hola. Thank you very much for that great talk. It was fantastic. We will open now the electron for questions. Estimados, todos pueden hacer preguntas en español si quieren. Voy a hacer mi mejor trabajo para poder traducir de ida y vuelta. Así que allá hay una pregunta. Por favor, chiquillos.
Okay, I'm from the St. John's School. Currently, I'm the captain of Beamline for Schools 2018. I'm in this science academy called Siemens, and we had a question for you.
Okay.
So, do you think it's possible to measure any gravitational wave or effect inside one of CERN's particle accelerators?
One word answer, no. The reason why is because in order to be able to measure a gravitational wave with any amplitude, you need massive objects, solar-sized objects. So, as I'm waving my hand here, I'm actually producing gravitational waves. you're being bathed by the gravitational waves in one hand. But the size of the effect is so tiny, so I don't think that, I personally don't see any mechanism by which we could measure something that's so.
Okay. Thank you very much.
¿Alguna otra pregunta?
It's possible that for instance, in very dense environment, like the core of a globular cluster, this event of very high energy gravitational wave influences the formation rate or the structure of the stars around some way, breaks some stars, this kind of things.
It's a good question. I don't necessarily have an answer for you. I would say that, first of all, there have to be a lot of gravitational wave production to be able to influence the way matter is distributing. So it's hard for me to see that might happen. I think it could work in reverse, though, that the dynamics of the globular cluster could produce configurations such that we could actually generate more gravitational waves. Again, it's because the coupling is so weak. Gravity is so weak. It's hard for me to see that's the case. I'm not going to rule it out, but I don't know. I don't know of any way that can happen.
¿Hay otra pregunta?
I'll think about that one.
What kind of secrets we can reveal using gravitational waves?
I'm sorry, what kind of
Secrets of the universe.
secrets? Well, okay, the big one is the Big Bang. So if we could detect gravitational waves from the Big Bang, we'd be able to have a better understanding of the process by which the universe was formed. I think that's number one. A really interesting one for me is, I started this talk by telling you that we rely on the theory of general relativity, which is Einstein's theory. And it's been right again and again and again. It's a 100-year-old theory, and it's never, ever met a test, experimental test that has failed. It always has been the right theory. At some point, we know that it can't be the right theory, and that's because there are four forces in the world, but let me turn it into theories. There's general relativity, and there's quantum mechanics, and there are two competing theories. Quantum mechanics tells us how the microscopic world works. General relativity tells us how things on universal scales work. People have tried for almost 100 years, literally, to bring those theories together, and they can't. There's just a fundamental problem with trying to merge the theory of the ultra small with the theory of the ultra big, and the ultra relativistic. So we know at some level that general relativity can't be right. We just don't know why it's not right, and right now we don't know how to fix it. My hope is that we will see something in our data, that our waves will tell us that there's a problem with general relativity, that it's not right, that there's a clue to how you might think about moving beyond general relativity. And we study gravity in its most extreme case, right? Near black holes. That's where gravity is really quite strong and nonlinear, right? So it's not unrealistic to expect that we might see something as we make better detectors that will move us in the direction where we can say, okay, Einstein's theory has gone as far as it can. And that would be very exciting, because that would, again, open a new window on the universe.
Okay, thank you so much.
Don Alexander.
My question goes to, by the size scale of supermassive black holes in some sort of galaxies, but will the collision of two supermassive black holes also produce kind of gravitational waves?
Yes,
Well,
yeah.
I guess very more powerful than whatever we expected.
Right, so yes, the collision of two supermassive black holes will produce a very energetic burst of gravitational waves. These supermassive black holes are, sit at the center of galaxies that are 10 to the 6th to 10 to the 8th solar masses, millions to billion solar masses. When galaxies collide, it is possible, and there's I would say, slight observational evidence for the fact that there might be found supermassive black holes. The problem, not problem, it comes back to the frequency of the waves, all right? They'll collide with a merger frequency of a microhertz or something like that, or even a nanohertz. So the time scale for which it plays out is much, much longer. And so you need a completely different type of detector. But people are actively looking for that, and it's possible that in the next 5 to 10 years, we'll have discovered evidence for the collision of supermassive black holes.
There's another one over there.
Hola, necesito traducción, por favor.
Por supuesto.
No me quedó claro, al momento en que dos agujeros negros colisionaban, se perdían 3 masas solares, si no recuerdo, y se transformaban en ondas gravitacionales. Eso quiere decir, la materia se transforma en... ¿Qué es la onda? O sea, ¿es como energía lo que ocurre? ¿Pasa a energía?
So in the collision of two black holes, the example we've shown, there was 3 solar masses that were being evaporated.
Right.
We would like to know what's actually happening in the process of that event.
What happened with the mass? Where it goes?
Yeah, it gets converted by this E equals mc squared process into basically energy, gravitational wave energy. So the conversion process is, if you remember the movie that I showed, all right, the space-time is warping really dramatically. And so energy, as these black holes collide, the energy is going into warping the space-time, right? And when the space-time relaxes, it produces this burst of gravitational wave energy. But it's done in a very predictable way. We can actually calculate this. So yeah, so if you think about it as these event horizons merge, all right, the space-time, because the curvature of space is so great, all right, within the event horizons, it's infinite. We don't know what's going on inside a black hole, but we're quite certain that there is something called a singularity, where the curvature of space-time is infinite. Right? As the two of them collide, the energetics of that collision is such that the geometry of space is radically deformed and distorted. And a huge amount of energy gets deposited in space-time that's outside the event horizon, and then that all relaxes and goes away.
Okay, thanks.
Acá hay otra pregunta.
So, which are the most important factors that we have to consider here in Earth to detect gravitational waves? So, because I'm sure that there's a lot of things here in Earth that affect the detection of these waves.
Good. That's not an easy question to answer, but I'm going to try and answer it in 30 seconds or a minute or less. It's really hard to make detectors on Earth that are stable enough and quiet enough to be able to be still. So remember I told you we're trying to detect displacements, changes in distance, a tiny, tiny fraction of a proton. How do I make a mirror that does not feel any other force? All right. So there's a huge amount of challenge in doing that. And the biggest challenge turns out to be the Earth itself. All right. And you guys know this because you live in what I would call an active seismological environment. And we have a lot of earthquakes. The Earth is moving all the time. So we spend a great deal of energy, brain power, money to make these interferometers that the mirrors are so quiet that they don't feel that vibrational motion. So that's really the biggest challenge. There are other challenges. You have to make the lasers that we make are the most stable lasers in the world. And there are teams of people that spend 10 years developing this laser. You have to put this whole system, in fact, I can show you. You have to put the whole observatory in a vacuum. All right. This is one of the arms. There's a pipe that's about this big that's totally evacuated. All right. And you have to make a vacuum system that's huge, and that turns out to be non-trivial to do. So there are a number of things, but those are sort of the big things, I would say.
Thank you very much.
Esta parte del público acá también, ¿cierto? Vamos a quedar la carne.
Hi, thank you for your lecture. My question is, if you can make an analogy with the electromagnetic spectrum, in which range would be these detections, these gravitational waves?
These would be gamma rays. Yeah, good. There's actually a lot, there's a good number of analogs between electromagnetic radiation and gravitational radiation. I can walk through them for you. First of all, light travels at the speed of light. Gravitational waves travel at the speed of light. At least we believe that, and so far it's been proven out. Light comes in two polarizations. Gravitational waves come in two polarizations. Light comes in different wavelengths. Gravitational waves come in different wavelengths. In our case, if you think about it from the astronomical perspective, right? You have at the high end you have gamma rays. We have gamma ray telescopes. At the low end you have radio, and then you have everything in between. We're the gamma rays of gravitational waves. We detect the most compact objects that produce the shortest wavelengths. Right? The Big Bang would be the radio waves. All right, it's the long wavelengths. The wavelengths of the gravitational waves in the Big Bang are literally fractions of the universe.
So the analogy is correct.
Yeah, I think it's quite good. Yeah. It's, in fact, it's just a different kind of wave.
LISA would be.
What's that?
LISA would be in which?
A laser?
LISA.
Lisa will be one notch below here. So, our gravitational waves have periods of milliseconds, frequencies of kilohertz. Lisa is here. So it has periods of basically hertz, less than a hertz to maybe a microhertz. So it's here. These are the supermassive black holes that this report is asking about, and this is the inflation rate. So.
Thank you very much.
There's a question here.
How did you identify that the origin of the gravitational wave that you measured comes from these collisions of these black holes?
Yeah, so all you get out of this detector are these two waves.
Yes.
Right. Okay. So the first thing you have to do is you have to convince yourself that they are of astrophysical origin and not ground. They weren't produced by the environment themselves. We have a number of ways to do that, which I could spend hours talking about. But the basic way we do it is that we do a lot of statistics. We replicate the data channels, and we calculate the probability of the event not being an astronomical event. And in our case, for those gravitational waves that I showed you, the blue wriggles, it was like 10 to the minus 7. Right? So we would call it a 5 sigma event. Right? So that tells you that you should trust it as a real event. But that doesn't tell you where the event is. It doesn't tell you about the masses. I don't want to spend too much time because I don't need to. All right, here, yeah. There's a huge amount of information coded in here. All right, first of all, right here, the waves die. So that tells you the merger's over. That frequency tells you something about the final mass of the black hole. All right, this chirp, all right, this sweep in frequency tells you something not easy, but it tells you something about the initial masses of the black hole. Once you know that, you roughly know the masses, then the amplitude tells you how far away they are. Then you have to rely on multiple sites. The fact that you have 2 different sites or 3 different sites, and that gives you the localization. So that's roughly how it goes. Roughly.
Another question?
Hi. Can you tell us anything about how you arrived to work in LIGO and how has your the large surge of gravitational waves along this large surge?
Yeah, you're asking a personal question about how
Yes,
I actually got
yes.
involved. Yeah, great, good. Right, so I was trained as a laser physicist, actually. I knew nothing about astrophysics. Right, but I took a course in college in general relativity. Right, and I fell in love with it. I thought this is a really cool theory. But
But when I got to graduate school, I decided I was going to be an experimental physicist for a number of reasons. And in 1996, the opportunity presented, actually, one of the guys who won the Nobel Prize, Barry Barish, came to me and through a connection of mine and said, "Are you interested in getting involved in this new field, gravitational waves?" And I said, "What is it?" And he said, "Well, we're trying to measure something, a tiny, tiny diameter proton over a 4-kilometer baseline on the Earth, and we have to build 2 of these detectors." And my first reaction was, "This is crazy. It will never actually work." And he said, "No, no, no." He said, "Study it. Look at it." And it was actually Ray Weiss who told me, look at the papers, because it's actually, we think it's doable. And so I read the papers, and the more I read, the more I said, "Yeah, this is kind of cool." Right? And I knew that it was going to be hard. So another question that I get asked all the time is, did you really think you would detect gravitational waves when you got started? And the answer is, of course. Why would I have done it if I didn't think we would detect gravitational waves? So when I heard about the experiment, I got really pumped, and that's how I got. That's why I stopped doing the other stuff I was doing and got involved in that.
Thank you.
Pregunta. ¿Podría?
Hello.
Hi.
Gravitational waves could be affected by massive objects in like galaxy clusters or supermassive black holes.
I'm sorry, I can't hear you.
Like galaxy clusters?
Sure. Yeah. Everything that's moving and accelerating, any object in a circular orbit is producing gravitational waves.
So gravitational waves could be affected by that?
Yeah, it's kind of, I think, the same question that was asked a little bit earlier. Maybe on a global scale, or a universal scale, large scale structure, it's quite possible, and I'm not an expert in this, so I'm going to remember this question and ask it to somebody I know when I get back to the United States. It's possible that the inflationary epoch, the universe, that the gravitational waves might have influenced early on the distribution of matter. The universe is very clumpy, right? I mean, there's places where there's galaxies and there's places where there's not. So it's possible that could have happened, but I don't know the answer for certain.
Intentar en español, no sé inglés. ¿El gravitón es una partícula real o aún es teoría? ¿Qué sucede con él?
Yes, absolutely. Well, okay. The question is the graviton a real particle? And the answer is, if you believe that at some point we will be able to come up with a quantum theory of gravity, the answer is yes. I believe that we will come up with a quantum theory of gravity, so I think at some point we'll be able to say that. I will point out, though, that you can calculate, if you say that you can write down the equation for a graviton. Basically, it's the frequency times of the wave times h, the Planck's constant. How many gravitons were released in this event? And the answer is 10 to the 70 gravitons were released in this event. So this was a very bright emitter of gravitons. But we can't detect gravitons yet, so we don't. Do you want to translate? Just say yes, gravitons exist.
Aprovechando como el tema del gravitón, si se supone que el gravitón es partícula, pues no debería tener masa, pero las ondas gravitacionales son un fenómeno energético. Entonces, ¿cómo sería como la conversión entre la masa y la energía para poder detectar las ondas gravitacionales? ¿O cómo se daría ese fenómeno?
How is the conversion between mass and energy in the gravitational wave release?
How's a conversion of mass and energy to gravitational wave release? I think that's maybe almost the same question that was asked earlier. You can think of space, I'm going to answer the question maybe differently. You can think of space as a spring, all right? And when I put mass into space, it sort of pushes the spring. Right? When these two things collide, these two black holes collide with one another, they actually stretch the space so much that they release the energy that's stored in the spring due to the black holes. It's released in the form of gravitational waves. That's a very naive analogy, but it's probably not bad.
El espacio-tiempo entonces se visualiza como si fuera un resorte que
mantiene energía guardada, ¿cierto? Entonces, en el fenómeno de la onda gravitacional, entonces este resorte va a absorber y entregar energía al medio y al espacio-tiempo. Y eso es lo que tiene una constante de tiempo también para la entrega de la energía y de la recepción de los fenómenos de dominio del tiempo, en esto como de la variación de materia. Yo creo que vamos a tomar una más y le vamos a dar un poco de descanso. Parece que van a hacer dos más.
Hi, Ligo here. Well, I have a lot of questions, in fact, but one of them is, do you think that this discovery is like the first step in the stair to understand or in fact to discover the dark energy or dark matter?
I'm not sure I understood the question. Ask it again. Do I think that
If the discovery of the gravitational waves is one of the first steps in this stair to discover, in fact, what is or how it works, the dark energy?
I have not myself heard of any theories yet connecting up gravitational waves to dark energy directly. I mean, dark energy also comes out of the Einstein equations. It's the cosmological constant, which I didn't show. So it's possible that there's a connection, a deeper connection there that we don't know yet. Dark matter is a different story.
Yes, I can imagine, because these waves are energy.
Well, so it's very interesting that right after we published our paper with those nice, beautiful waves in them, a very prominent group of theorists predicted, basically they said that the black holes that we were detecting were in fact dark matter. You know, black holes are dark, right? They can't be detected, so that's not right. And they made some predictions that personally I don't think I think it's a stretch. You know, I'm going to say that I don't believe it, but it also makes some predictions about what we call a mass spectrum of the black holes. And after we see, hundreds of these collisions, we'll start to know if maybe these black holes are some, not all, but some of the dark matter that's being created. As dark matter moves, if it gravitates, and we believe it does, it should produce gravitational waves. So, it's a question of which detector will maybe see it. I don't know. But I can assure you that if there's anybody who's thinking about this and comes up with a good idea how to detect it, we will try and look for it. I guarantee you.
Okay, thank you.
Y la última.
Hola. Hemos visto que dos objetos masivos que producen ondas gravitacionales. Mi pregunta es, ¿el Big Bang produciría, no estoy seguro, produciría ondas gravitacionales? Y si en teoría antes del Big Bang no había espacio ni tiempo, ¿de qué manera produciría esas ondas gravitacionales que se podrían captar en teoría?
The Big Bang could produce gravitational waves, and then the next one is more complicated because it refers to the situation before the Big Bang.
Okay. All right. So the first question is easy. Yes, we believe the Big Bang produced gravitational waves. We haven't yet detected them. Second question isn't easy, but I have an easy answer for it, and the answer is we don't know what happened. There are models for cosmology called pre-Big Bang models that have some predictions, all right, and it mostly relates to something called string theory. It's possible that we, using LIGO, could test some of those models. But I haven't looked at it enough to know if there's a good set of data that we could use to test those models. So the short answer is, what came before the Big Bang, we don't yet.
Vamos a ocupar toda nuestra masa y nuestra energía en agradecer a